Hello everyone, this is part 2 of power series solutions to differential equations. We left off here with showing if we assume that y is the power series as a solution, here's its derivative. Note the change in index and how we basically just differentiated this, treating c sub n as a constant. Another thing we're going to need to determine our solutions using the power series method is what we call the identity principle. Notice that these two sums are equal. If these two sums are equal, then you could set the coefficients equal. So the a sub n and the b sub n can be set equal to each other. But notice that the n's have to match on the power on x, and the indices have to match as well. Doesn't really need to be 0 all the time, but as long as the indices match and the powers on x match, you can equate the coefficients. And then this one is just kind of like a little corollary. If you have a single series set to 0, then you can set this coefficient to 0. Alright, there's one last thing we'll need. And that is, so we need to know the derivatives, we need to know the identity principle, and then there's what I call the shift of the index of summation. So we might have to adjust our starting point. In particular, like when we substitute y prime in, and if we have a y involved, we have to make these indices match in order to be able to use the identity principle. So here's one example of a situation where, let's say we had the sum as n goes from 1 to infinity of n c sub nx to the n minus 1. That's essentially a first derivative. If we decrease the starting point, if we decrease the index by 1 to start it at 0, then basically we compensate by increasing all of the factors of n, or all of the terms involving n, in our expression for this nth term. So notice how we decreased the n by 1 to make it 0, and this n, and every n in here, was increased by 1. That is, this n became n plus 1, the c sub n became c sub n plus 1, the x to the n minus 1th became x to the n plus 1th minus 1th, which is just x to the n. Now the reason why that's true is if you look at the sum as n goes from 1 to infinity of the n c sub n x to the n minus 1, and you expand that, when n is 1, this would be 1 c sub 1 x to the 0, and x to the 0, of course, is 1, because this is n minus 1. So we just get c sub 1 for the first term. For the second term, when n is 2, we'd get 2 c sub 2, x to the 2 minus 1 is x. For the next term, we'd get n is 3, so we have 3 c sub 3, x to the 3 minus 1 is 2, and so on. And that is equal to the sum as, let me move this over, or let me do it this way, plus dot dot dot, and then equal to the sum, if we start at 0 to infinity, the constant, the subscript of 1 has to be obtained first, and this coefficient has to be 1. So therefore, if you add 1 to the n plus 1, I'm not going to be able to squeeze it in, so I'm just going to argue it below. that n would become n plus 1, because then when n is 0, you'd get a coefficient of 1, and the c sub n becomes c sub n plus 1, because then when n is 0, you get c sub n. And then this can just be x to the n, because when n is 0, it's 1, and then that gives you all of these terms. Because when n is 1, this becomes 2, there's a 2, n is 1, this becomes c sub 2, there it is, and x to the n is 1, becomes x to the first. You could verify for n equaling 3, and so on. We could extend this idea. For example, you could drop by 1 unit, you could drop by more than 1 unit. If for some reason you ever had n equaling 3 to infinity of, let's say, in general, a sub n, x to the n minus 1th, then if you wanted to drop down to, let's say, 1, okay, that would be a decrease of 2. So to compensate, we increase the value of n by 2. So this becomes a sub n plus 2 times x to the n plus 2 minus 1 would be n plus 1. And it can go in either direction. You could decrease the starting point, or you can increase the starting point. Let's say you wanted to go from, you started at 1, and you had, I don't know, n c sub n, x to the n minus 1th, and for some reason you wanted to start at 3 instead. Okay, but now it's an increase of 2 in the starting point. So to compensate, we have to decrease this value of n by 2. So the n becomes n minus 2, the c sub n would be c sub n minus 2, and then the x to the n minus 1th becomes x to the n minus 2 minus 1, or n minus 3. Okay, so just a little shift again. Decrease the starting point, you increase the value of n's in the nth term. Increase the starting point, you decrease the values of n in the nth terms. And then the last thing, which I probably won't test you on, but it's in the homework and I'll show you how to find it. Given any power series, we're going to let rho be equal to the limit as n goes to infinity of the absolute value of c sub n over c sub n plus 1. And this is what's called the radius of convergence. And if rho ends up to be 0, then the series diverges for everything except 0. If rho is between 0 and infinity, kind of an odd thing to say, but that's the way the textbook rates it. So the odd thing is the less than infinity. Then the series converges if the absolute value of x is rho, the absolute value of x is less than rho, and diverges if the absolute value of x is greater than rho. And if rho equals infinity, then we have convergence everywhere. So we'll just be asked to find the radius of convergence in the homework, and we'll do so as an example, but I'm not going to test you on it. Okay, so now we get to put everything together. And our example is something pretty simple. Y prime is 4y. But we want to find the power series solution, determine the radius of convergence, and identify the series in terms of elementary functions. Okay, so we assume that y equals the sum as n goes from 0 to infinity of c sub n x to the n is a solution. then that means that y prime, so this is what we established earlier, is the sum as n goes from 1 to infinity of n c sub n x to the n minus 1th. Okay, so that's the way basically we start every problem, just by making the assumption that that power series again is a solution, and we know what its first derivative is. So then we just simply substitute in terms of the power series now. So y prime, once again, is the sum as n goes from 1 to infinity n c sub n x to the n minus 1th. And that's equal to 4 times y, which is the sum as n goes from 0 to infinity of c sub n x to the n. Okay, now what I like to do here is this. Make a little note off to the side. It doesn't have to be in a different color, but I'm just doing it in red here. And indicate how the powers of x compare and how the indices compare. So I'm going to say here that the powers of x differ by 1, because this is n minus 1 and this is n, so their difference is just 1. And then the indices, or let's say the n values, also differ by 1. And if the difference between the differences of the power, how the x powers differ and how the n values differ, if these are the same, then you can get away with a shift. And you could shift either one. You could shift down, you could shift up, but it's typically more desirable to shift down. But if these are the same, a shift is going to make it such that we could use our identity principle. Because notice we can't use the identity principle now, because the powers on x are not equal and the indices are not the same. But if we shift this down, by 1, then let's see what happens. Okay, so if we change the starting index to 0, then we're going from 0 to infinity. Okay, so remember, compensate. If I decrease the value of n by 1 in the starting point, I increase the value of n in all of the factors involved in the nth term. So all of these n's become n plus 1. So therefore n now is n plus 1, c sub n is c sub n plus 1, and x to the n minus 1 becomes x to the n, because it would be x to the n plus 1 minus 1, and the negative 1's cancel. And then that's going to be equal to, and we could leave this side the same. And now look at the indices. They're the same. And the powers on x are also the same. So therefore, we can apply the identity principle. And here's the easiest way. Just take everything except the sums and the x's. Don't forget this 4. and set them equal. Basically just drop the sums and drop the x to the n's. And then we have n plus 1 times c sub n plus 1 is 4 times c sub n. Okay, and then what we're going to do is we're going to solve for c sub n plus 1. And c sub n plus 1 would be 4 c sub n over n plus 1. And this equation is what's called the recurrence relation. So that is what we need to do, is compute the values of c sub 1, c sub 2, c sub 3, etc. in terms of the leading term c sub 0. So here's what we do. We take 4n equaling 0, 1, 2, 3, ... to the recurrence relation. If n is 0, c sub 1 would be 4 c sub 0 over 1. Because all I'm doing is I'm plugging a 0 in for n here. So 0 plus 1 is 1, set c sub 1. And there's 4 c sub 1 over, or c sub 0 that is, over 0 plus 1. So 4 c sub 0 over 1. Or let's just call it 4 c sub 0. Now we're going to let n equal 1. When n equals 1, we get c sub 2. And that would be 4 c sub 1 over 1 plus 1, or 2. But c sub 1 is 4 c sub 0. So this would be 4 times 4 c sub 0 over 2. Or, let's say 4 squared over 2 times c sub 0. Now, you usually have to do about, I don't know, typically 3 or 4 of these are probably going to be sufficient. So let's do another one. C sub 3 would be when n is 2, and we'd get 4 c sub 2 over n is 2 plus 1 is 3. But now c sub 2 is, that's why we call it a recurrence relation, because we're always going back to the previous one that we found. This would be 4 times 4 squared, or let me do it this way. Just want to make it clear. It's going to be the 4 thirds times 4 squared over 2 c sub 0. Because the 4 squared over 2 c sub 0 is c sub 3. But then consider, that would make it 4 cubed. And then this 3 times 2 should remind us of 3 factorial. Alright, and let's do c sub 4 as well. Okay, c sub 4 would be when n is 3. We'd have 4 c sub 3 over 4. That would be 4 over 4 times what we just found. Oops, I lost my c sub 0 there. Sorry about that. 4 cubed over 3 factorial times c sub 0. But then that would be 4 to the 4th over 4 factorial. Because 4 times 3 factorial is 4 times 3 times 2 times 1. Or 4 factorial. So there's the pattern. And so now we need to express our function y in terms of these coefficients. Now, y is the sum. This is what we assumed was the solution, right? The sum as n goes from 0 to infinity of c sub n x to the n. But in expanded form, that's really just c0 plus c1x plus c2x squared plus c3x cubed. I don't know if you want to go further. Maybe we could even go further because we did actually get 4 of these. C sub 4x to the 4th. Okay, so that's the general solution at all times. It's the assumption that we made, that this was a solution. Now, if we replace the C1 by 4c sub 0, and we'll replace C2 by 4 squared over 2 c sub 0 x squared plus c3, 4 cubed over 3 factorial, we said, c sub 0 x cubed, and then if you want this extra one, 4 to the 4th over 4 factorial, c sub 0 x to the 4th. We can certainly tell what the next term's going to be. Now this 2 is really, you can call it a 2 factorial. But what we're going to do at this point is factor out the c sub 0. And then we have 1 plus 4x plus 4 squared x squared over 2 factorial plus 4 cubed x cubed over 3 factorial plus 4 to the 4th x to the 4th over 4 factorial, and so on. Okay, and so then we want to express this series in terms of an elementary function, and if we look at the denominators, they are all just factorials following the natural pattern of 0 factorial, 1 factorial, 2, 3, 4 factorial. Looks like an E. We have sums, powers match. Only issue is the 4s, but that's why we went over those examples from the last lecture. We can express this as 4x quantity to the first plus 4x quantity squared over 2 factorial plus 4x quantity cubed over 3 factorial. If you want to go further, 4x quantity to the 4th over 4 factorial, and so on, which would then be c sub 0 sum and goes from 0 to infinity. Instead of x to the n over n factorial, it's 4x quantity to the n over n factorial. And then we see that this is our elementary function e to the x, but where x is 4x. So this would be c sub 0 e to the 4x. So that's our solution. Again, I'm not going to ask you about the radius of convergence, but just to do it the one time, so you could do your homework. Radius of convergence, rho, is the limit, n goes to infinity, absolute value, c sub n over c sub n plus 1. And basically that's the limit as n goes to infinity, absolute value. Okay, you could leave the c sub n in the numerator, and in the denominator, c sub n plus 1 is basically our recurrence relation, what we found up here. 4c sub n over n plus 1. So we could substitute the 4c sub n plus 1 in the denominator, and then the c sub n's cancel. Reciprocate this, we get the limit as n goes to infinity of, I'm going to drop the absolute values because nothing is negative, n plus 1 over 4. And you could say by inspection that approaches infinity, because you get infinity plus 1 divided by 4, so rho's infinity. And then if you look back at the definition for rho, we could say that the series converges for all values of x. Okay, so there are a couple more tricks. We got 2 more examples to finish off this section, and so we'll come back and hopefully finish both of those in the time it takes for one nice half-hour video.